All right, let's talk about schedule because there's a lot of strange happening. Let's see if I can do this justice. This the okay. So for this week, obviously we meet today and tomorrow. I'm going to get a study guide to you today because we are going to need to have a quiz on Monday. It is the only day left that we don't have an in-class activity of some kind, because next week's Tuesday and Thursday, we're going to have some guest lecturers who are some of the cyber candidates in our class. And I think that Thursday, there's some other event in this classroom, so class is going to be in 301 instead of 304. I'll send out an announcement about that. So study guide. Tomorrow is also going to be peer reviews for this first week, but there will be no peer review next Tuesday. We will instead have the final peer review over finals week as being the last, how did everything go leading up to the sprint 4 deadlines. There will still only be 2 peer reviews. And that means that I anticipate that people are going to be spending and taking some time for Thanksgiving and being with family. So there's no peer review over that period of time. I don't want to think that would be fair to anybody. Does that make sense? Is that fair to everyone? And then we have a finals slot where we're just going to be coming in and doing that quick presentation. I would recommend that people take the rest of that time and work on some final code, because there'll be the final code. Let's bring this out into a calendar. Maybe it's even worth writing it out as a calendar. That'll make it visual exactly what's happening and when. So we're doing calendar. We have today, which is Thursday. I think I made that final. All right, Thursday. We meet on Friday. This week, next week, and finals. So, wish I could draw a turkey. This is turkey week. This is last week of classes, and then finals. So, tomorrow, this is Monday, Tuesday, Wednesday, Thursday, and I guess we technically need a Sunday for a deadline. So Tuesday is peer review. This is study guide. This is quiz. 4. We have guest lecture. We have client demo. We have guest lecture. And then someone told me what our final slot was, but I already forget it. I think it was Thursday of finals week. Is that right? Thursday, did you say 1 to 3? Is that right? Or is it some other time on Thursday?
It's earlier.
Earlier?
Check, is it in the syllabus?
It's not in the syllabus, but these things can occasionally change. So I can make that announcement now if we go identify exactly. I'm pretty sure it is on this last Thursday. So this is going to be,
I think it's 10:30 to 12:30.
10:30 to 12:30.
Those are just presentations, correct?
Yeah. And again, they're graded on pass to fail. I would anticipate them being under 20 minutes, but I want them to be involved enough that what they should be is not a bunch of prepared material necessarily, something that you should talk about as a group, but give a short presentation on each sprint. What happened in sprint 1? How did you feel about it? What did you learn? What happened in sprint 2? How did you feel about it? What did you learn? Kind of go through that process, and then eventually you will get to the end of sprint 4 where you can have an actual working demo of your project to say, here is our UML editor, here's everything that works. And then this Sunday here is, wait, this is not Monday, but Sunday. That's sprint 4. And then this Friday is final code. Remember that there's nothing new in the final code requirements. This is just an opportunity to fix some things from sprint 4 because there are no classes meeting at this point, and the only person our grader has to report to for anything this quarter is me. I think we can turn around sprint 4 really quickly. So my goal is to get you feedback on sprint 4 here so that you have these days to make any changes that you'd like to before that sprint 4 grade becomes the grade for your final code. At this point, really, I'm just looking at features. So I'm not really going to be looking for the Discord activity and the every other measure within that rubric. I'll just be looking at what did you get working? What did you fix? And you get some other stuff working ahead of that final code. That's kind of a look at everything that's left in this class. Questions or comments or concerns about the schedule?
How many magic the gathering packs would it cost to not have to take that quiz? Like, are we talking over 12?
We're talking, I am very unbridlable, which is
You want an original print of Black Lotus? I see it. There, bro.
the one ring.
Dude, I've seen it for 450 on Marketplace. Or do you want the actual one?
I want the actual one
Okay.
ring. The one person who owns it, you have to convince them to sell it.
Oh, he wouldn't be selling it. I'm breaking into Post Malone's house.
That's the point. I did not
That's
suggest
what's
that you
going
do that.
I feel like an actual violence.
You want the ever so mythic Black Lotus coaster?
All right,
Post Malone too. So. Paid $2 million for it, crazy.
other discussion items?
Is this an act of malice on your part, or are you just mean without trying?
What I really want, so the reason I've done sprint 4 and final code here is I want people to be able to use this in their code portfolios. I've been meeting with my own advisees who have gone through past versions of this class to make their own project. And for all of them, it's half-baked. It's something they got half finished. And they are saying things like, I would like some extra things to add to my code portfolio because I'm not happy with my code portfolio. I don't want to put you in that situation as a graduating senior, as you're about to go out into industry. I want you to be proud of everything that you made, and I want you to have something that will get you the job that you want. So I think that there's a lot here. These guest lectures aren't really going to be terribly involved. It's just preparing for a quiz. And again, I don't think this quiz is going to be the end of the world, challenging or difficult. It's mostly going to be, do you understand most of what we have covered since the last quiz? And then chapters 5 and 6 of debugging teams. Pretty straightforward. Other questions? Right. Racer broke. Slide down from flying. All right. Last we talked, we were talking about how to prove a program formally. So to do this, we have to bring back everything we know from discrete. We have to bring back things like proof types, things like propositional logic. So here we have some propositional logic. If the premises are true, then the conclusions are true, which means the premise implies the conclusion. We talked about four triples. We talked about these, which ones of these were true? The first two were true, the second one was false. It's just do the premises and the code imply the conclusion. We talked about preconditions and postconditions, something that we guarantee to be true before the code runs. That's a precondition or something that needs to be true in order to guarantee that the code results in the postconditions. And then the postconditions, what is true if the premises were true and we ran this code. So composition is now we're going to throw multiple statements together. So our programs are no longer a single line, like they were in the prior examples. Now we want to be able to have something work for an entire code segment. So what needs to be true? What is the precondition? So that with an implication, the post condition is that we were able to execute both S and T. So now we just have an and. If we have a precondition, run line S, then we run line T, then we can guarantee R. We basically need some middle ground, Q, that is the post condition from S and the precondition for T. So the post condition for this becomes the precondition for that. So we can show that if the precondition is true, we run S, we get Q. If Q is true, running into T, then the post condition to that is R. So now we have a precondition and a post condition for an entire sequence of statements. We just have to break them down into the intermediate steps where we know what's true at the end of each one of those steps. Questions on that? Then next we can dive into conditional statements. So conditionals can really be broken down into, as long as it's just an if else and not more complicated than that, we can show that we have a truth value now in our if statement. So we have a precondition, the logical inside of the if, the statement that gets run if B is true, the statement that gets run if B is false, and then we want some post condition associated with the entirety of the if statement. So how do we represent this in propositional logic? We can show that if B is true and the precondition has been met, and we run S, then Q is true. And all of that needs to be true in a statement in order to guarantee that post condition. If B is false, P is true, the precondition is met, and we execute T, then Q is true, or we get that post condition. So it's a guarantee about both paths through that if statement that allow us to state that after this if statement has been run, then the post condition is met. Questions on the conditional? So it's something that you know, the structure of a conditional, but now thinking about it in terms of how do we guarantee that something is true, that a certain property of our code is true at the end of that statement. We need to express that as a post condition. Loops get gross. So let's talk a little bit about loops and how this works. So the precondition for a loop is known as a loop invariant. It's something that's true at the start of every execution. Sorry, it's true at the beginning of that loop. So B is going to be the logical statement that is true. If it's true, we continue to execute the loop body. As soon as B is false, then we move to the post condition. The post condition now says that B by default has to be false, because otherwise we would have continued going through a loop. And then some other post condition gets anded to that. Both of them have to be true. So we can just append this not B to the end of that. So if executing S preserves P, then we end up with something that preserves some kind of rule or some kind of state that is going to be true both before the loop begins and after the loop ends. So that is called a loop invariant, something the loop does not modify throughout the execution of that loop. Stays true throughout this whole process, stays consistent. However, there's a problem, and unfortunately, a lot of you have not seen the concept of the halting problem. Take compilers from me if you want that in significantly more detail. So we don't necessarily know that all programs terminate. The reasoning behind this, take compilers, we can figure it out. If you're using manual verification, that's fine. But if you're trying to use automatic verification, there is no way to actually know that a program that we feed this verifier is actually going to terminate. If it terminates, we know that it terminated. If it has not terminated yet, what does that mean? Is it an infinite loop? Or is it eventually going to terminate? You can imagine writing an algorithm like BOGO sort, where you have an array, you're going to randomly permute that array and then check and see if it's in order. If it's not in order, you're going to randomly permute the array and check if it's in order. If it's not in order, you're going to randomly permute the array and check and see if it's in order. This is a factorial time algorithm. It's absolutely disgusting. Any array longer than about 20 isn't going to finish in a reasonable amount of time. Anything longer than the low 20s isn't going to finish before the sun envelops the earth. So now imagine that you take in an execution of a program and you don't have access to the source code. You don't know if it's spinning and spinning and spinning, if the algorithm that was passed in is BOGO sort on a long array, or if it's something that's in an infinite loop. You can't tell the difference from just the execution of the program. You actually have to look at the source code, parse the source code, and have some way of saying, oh, of course, there's a while true in here that is never going to terminate. So the concept of partial correctness here says that anything that finishes will be correct. As long as the program completes, the answer will be correct. But if the program does not complete, then we don't care if it was working towards something that would have been correct if it could have terminated. For some reason, it couldn't terminate. Total correctness tells us that all programs will terminate, and they will terminate with the answer. Excellent. Trivially partially correct program. Does this work? Well, every time this program halts, it's correct. How frequently does it terminate? Never. That's a fun correct program. This is why we care about the difference between partially correct and totally correct. This is the world's easiest partially correct program. It just never terminates. All right, so how do we actually handle loops? With the unfortunate part of loops, we can only really ever establish partial correctness. It is impossible for us in general to establish total correctness with loops. Again, I'll go into that in way more detail in theory of computation portion of compilers. But to generate partial correctness, we just have to be able to say, okay, we know the precondition is true. We know the condition on the loop is true going into the loop, so we execute it at least once. If we do this and we execute S, the body of the loop, then we know that the loop invariant maintains. So if that is true, if we can show P and B S P, then it's the equivalent of the precondition, the loop invariant is true, while the loop is true, do the code. Once that is completed, then B is false and the loop invariant remains true. Does that make sense? It maps to what we've done with loops, but it would be how we have to now verify a loop. If we wanted to say that for an arbitrary number of executions of a loop, this loop invariant is maintained throughout this, we actually have to go verify that this is indeed the case, that this for triple is true, because we don't guarantee what's going to happen with our programs if this is not true. Questions on this? Is this clear? Sets of thumbs? Yeah. Question?
So basically, we just have to assert that it actually loops, and we know it's true.
Well, we have to be able to figure out what is P. What is this thing that's true before the loop and after the loop, regardless of what the loop does. So that allows us to verify what this is. And that allows us to say, all right, well, as long as this loop terminates, then we adhere and still have this loop invariant. But if this loop doesn't ever terminate, we don't ever get to this point. We can't ever assert that this is true because the loop process never finishes. So this rule establishes partial correctness for that reason. Any other questions? All right, so how do we do it? Let's first figure out, what is this doing? What is this program actually doing? But could we figure out what those loop invariants are? And we want to figure out and ensure that this is actually a correct program, that it does what it's supposed to do. How would you state that in for logic? Masterclass and why you name your variable something that's in a single letter. What's funny is the algorithm's really simple, but it's obfuscated through the variable naming conventions.
Well, I got bored of reverse engineering stuff.
I love that. Anyone think they know what it does?
I
The
didn't get,
letters mean something.
I didn't get to the very bottom, but we have an assertion that n is either 0 or greater, so it's and d is always greater than 0.
That's what needs to be true in order for this process to work.
Then we set q to be 0. Okay, so that's a precondition. R is then set to whatever we have inside of n, and then the loop only runs if R is greater than whatever d is. Which means,
What are they? What are R and D?
Is it remainder,
Yes. It is.
denominator?
Yeah, we have divisor. So we have the number, the divisor, the quotient, the remainder. This is division. Very nice.
not about it, very good work, Kate.
So now that we've analyzed this program to see that what we're going through is kind of a step by step, we're going to be saying, okay, we want to divide some number by another number. So we're going to repeatedly subtract as we figure out how many times it goes in, as well as what's left over at the end. So at the end of this, the question is the quotient the number of times it went in? Do we end up with q times d plus r to be able to recreate n? Because we're passing in d. We have n divided by d equals q. So we should be able to reproduce and say that q times d plus r is n. The postcondition also states that the remainder must be between 0 and the divisor. 0 inclusive, the divisor exclusive. That makes sense. The remainder is between 0 inclusive and the number -1 inclusive. How would we know that this code actually works? But we have to go through this process of, all right, what is not changed through the course of this loop? What is the precondition for this loop? We know that n needs to stay greater than or equal to 0, and d needs to stay greater than 0.
Well, if you think about it by assignment, n and d never change throughout the entire runtime.
Right, so we don't modify that. So it becomes your loop invariant. So we go through this process, and now we have the assignments. So each execution of this loop, we can now use as a composition and say, can we make some statement about what happens inside of this loop for every execution of this loop? What happens? And then you keep that inside of your loop logic and your loop invariant until this ends up not being true anymore. So is that the case? So let's look at it in more detail. This is what it would look like.
Can we expect to see this on the quiz?
No. Anything that I target with this will be at a high level. I'm not gonna have you go through doing a whole logic proof. If you wanted to do that, take what should be discrete part 2 or discrete, like a discrete applied to computer science proofs type of class that doesn't exist, but I don't know, it should, but it'd be very under-enrolled.
You can get like 6 minute stops.
Compilers is kind of like this a little bit. It is not quite this level of detail in places, but it's abstracting it to try to understand how does a computer work? How does the translation process of going from a high level language to a low level language, what is involved in that process? It is kind of similar to this level of logic, but a little bit different, a little bit more problem solving, a little bit more fun. So you break it down into each line, and each line within that loop process that has a loop invariant outside of it, and the lines that are executed inside of it. So who checks the proofs? We write the proof down, but how do we know that that proof doesn't contain a mistake? Well, you are the first line of defense, so being able to read a formal logic proof goes a long way in something like a pull request. If someone is arguing with you and saying, my program is correct, it works, and you're having trouble coming up with a counterexample that shows this doesn't work on this particular input or for this particular reason, you could construct some kind of proof that shows that their execution is wrong. You can say, what is the precondition? What is the postcondition? Break it down into its steps. This beginning does not imply this end. There are, of course, also proof verifiers. You can use software to verify, but you have to be able to state the preconditions, the postconditions, etc. So you'll need to have an understanding of your program to make sure that you are verifying what you want to verify. So there's a minimal logical core, just makes assumptions about equality, about logical rules like modus ponens, etc. Nice and trustworthy. However, if we want to build something like this, if we want to figure out how to automatically verify a program, we need to start thinking about how do we work backwards through this process. So we're going to need to go through this concept of a weakest precondition. So we don't know what the precondition is. Let's say that we have some code and we want to figure out when is this code going to produce this particular postcondition. Usually when you write a program, you know what you want the program to do. I want this method to sort this list. So the postcondition is really easy to write. The list is sorted. The code that you write is your best guess at what implements this process. Now the question is, what are the preconditions? What needs to be true in order for this code to produce that postcondition? To do this, we need to figure it out or talk about it. So the weakest precondition is going to be a function that takes in the code and the postcondition and will spit out something that is the precondition for that code or that postcondition. How do we do it? Usually there are multiple paths through code. if we can figure out which path, basically a statement that said, if this path through this code generates the post condition, then all paths through this code generate this post condition. That's a lot less work than verifying it for every possible path through the code. So the concept of a weakest precondition is just stating, what is that path? How do you find that path? So it's true by definition, right? We just talked about how a Hoare triple works. This function will be that precondition if this statement is true. So we can phrase this in terms of an implication. If the precondition implies the weakest precondition of C and Q, then we get our lovely Hoare triple precondition code postcondition. You get a nice special case if your precondition is always true. That would be nice. If you can show that the precondition implies the weakest precondition, then you can prove the program is correct. So weakest preconditions become a very important part of that process. So how do we do it? Let's see if we can do it for assignment statements. And then we'll figure out how to work through something like a conditional. But what is the precondition such that if we execute the code x equals 5, then we get the postcondition x equals 5? When is this process true and when is it false? If it's always true, then the precondition is true. So that is the case here. In every world, if you assign x to be 5, then x equals 5. Immediately right after that. Can't have it any other way. Now the question is, what is the precondition for if we say the postcondition is we're going to assign j plus 1 to be a, the code that we execute is j plus 1. What is the precondition? Sorry, we bump up j by 1. What is the precondition such that this postcondition is true? What needs to be true ahead of executing this statement in order for this to be true? Note how this is the exact opposite question I asked you a while ago.
The A equals J.
Yeah, so if a is equal to j, we bump up j by 1, then a is equal to j plus 1. This really, in Java, should have a second equals. But in a lot of other languages, just saying that a has the value of j plus 1. If a has the value of j before we start, then this is true. If a has a value that is not j, then this doesn't hold. How about this? So we want I to be greater than j at the end. The code is if I is greater than j, then I is equal to j.
Trying to get the post condition to be true.
Yes, the post condition at the end of this statement needs to be true. So what needs to be true here in order for this code to produce that result?
Logically, there's nothing you can do.
That is not true.
I just agree with J.
Close. Logically invert that.
I is less than J.
If I is less than or equal to j, this is false. This never happens. Uh-oh, I is still less than or equal to j. That would be nice, right? So let's say now that I is greater than j, then we're gonna set it equal. That can't happen. So this is an example of a person who said, person who said, this can't be, there's nothing that allows us to get that result. That's intriguing. Right? Now we have an example of a place we would like to be able to get to, some code, and we're able to show that in no world can you produce something such that when you execute this, you get there. The code is right for no possible inputs. Intriguing. So the weakest precondition for an if-then statement ends up being, look at the paths through that. There are two different paths through this, when this is true and this is false. You're going to look at those two paths, and you're going to try to figure out, okay, how do we get there from one or the other? But it's going to get much more interesting. So if it's true in no possible world, you just put false. Loops end up being weird. Weakest precondition can be easily mechanically derived for anything other than loops. General loop invariants are very, once you have that invariant, you can check that invariant, but deriving that invariant, that is really tricky. It's very difficult to automatically to write a program to take an input, a loop, and be able to generate that loop invariant. You don't even have to be trying to prove whether that loop terminates or not. Even if you know the loop terminates, it's still a difficult problem. So loops are the sticking point in programs that make automatic verification very difficult. So how are we going to do it? Here's one way you can unroll a loop. Right? You basically take a while statement and you can turn it into a repeated if statement. Okay, let's say that we can do this. Great. When is this going to be equivalent to this and when will it not? When is this actually equivalent? I guess it is still equivalent, right? If and an if before a while. So if you try to assert at the end of it, not e, that will work for all iterations of this loop when you have two iterations or fewer. You could change this two ifs into three ifs, or four ifs, or five ifs. But the idea is you have to pick some number, some constant number of ifs to try. If e body, if e body, if e body, whatever number you pick is going to work for all instances of this loop with that many or fewer iterations. As soon as you have more iterations than that, then you needed more if statements. And there's always going to be some counterexample of what happens when I run this loop one more time than whatever it is you decided as the number of if statements that you needed. Then you no longer have a guarantee of your program's correctness. So you can make a partial guarantee about some number of loop iterations by breaking a while down into a sequence of ifs. But that's not always going to cover every case. So you can do this and the program will verify executions without more than that many loop iterations. So that's one way you can partially prove things. So if you use bounded software model checking, BSMC, then you use weakest precondition. It takes any loop and you're going to tell it how many times to unroll it, and you can get that partial guarantee. of all instances of this program where this loop doesn't run more than this many times consecutively, then we guarantee the result. But we can also take into account the loop invariant. So this concept P, we call the loop invariant. As we choose our loop invariants, we can make more complete statements about our programs. So if you make a loop invariant that is too specific or too general, you may not be able to actually prove what you're trying to prove. For instance, if your loop invariant is true, just the logical concept of true. Of course, true is still going to be true at the end of your loop, no matter what your loop does. So that is the most general loop invariant that is never useful. You may ask yourself a more complicated question, like after this loop iterates, is the value of A less than or equal to 3? So you may be able to answer that via bounded model checking for iterations of 3 or fewer or 4 or fewer, etc. But you can get too specific as well. So too general, true. Too specific, I equals 10 arrow P, where we are no longer able to verify something we care about. So there are lots of ways we could try to generate a reasonable loop invariant, but the difficulty is picking that loop invariant that's going to be able to prove the code is true in a meaningful way. Says something about the code. So we want to abstract the execution of this program into domains. So as an example of a domain, a sign domain, your variable is either positive, negative, or 0. If you could make a statement about, maybe you can prove the end result is positive when, and now you can go through a loop invariant and show that if this is true before this loop starts, then the end result of this variable is positive. If something, then the end result of this variable is negative. If something, the end result is 0. This basically just turns into a proof by cases, where you break down into all possible cases of what the variable could be. If you can prove them each independently, then you prove that idea in general. So now we get something like, if x is 42, y is negative 3, and z is 0, then we can show x is positive, y is negative, z is 0. Great. That doesn't tell us anything about the loop associated with those, but now we can at least imply something about their sign domains. So we abstract these values into these concepts, and then we can prove something about those concepts rather than the exact values of those variables. So here's an example. After this code, we care about I and we care about sum. What can we state about their sign domains? They're positive, right? There's no way for either I or sum to ever be 0 or negative. Even if we wanted to show something like this program is correct, that's going to be a lot harder, but an easier question to answer would just be something like, at the end of this loop, are I and sum positive? That's a lot easier to show than trying to figure out the exact value that they might be. So this is an abstract interpretation of this code. Microsoft has lots of ways of verifying. You would imagine that any company that creates something as complicated as an operating system and as widely used as an operating system and as vulnerable as an operating system, that you might want to verify some certain properties about it. So they generated Boogie, a language designed for verifying programs. It'll read a program in Java, convert it to Boogie. And this process is based on these verification conditions. Here would be an example. The execution, is this property always true? Does this procedure always return an int? We can check and ensure that n is greater than 100. If that is if that is true, then is r equal to n minus 10? Is that something that we can verify? So we can use the keyword ensures to just go through and now execute this code, and it will verify saying, yes, everything that you asked is true. So it uses exactly these concepts to go through and actually verify your program. It gets a little bit harder when you have things like loops. So we have some insurances, our post conditions, that are pretty complicated. And now we could actually go look at the bubble sort algorithm and try to ensure for all I and j, set I to 0, etc. We can set invariants. Invariants are things that we said needs to be true before the loop starts and after the loop ends. So we will list all of our invariants. And you can see that it can generate some of those invariants as well. So we state them, and we're able to actually go verify. We don't actually see the verifications here, but it's pretty cool. Unfortunately, this process is so involved that, especially for large scale programs, something like an operating system, it's very expensive. It would take way too long, be way too difficult. If you write something that is very simple, or if it fails, there's not a huge problem associated with it, then the amount of work that you put into it is just not worth the guarantee that you get back on the other end. If you were to ever find a bug with that, it would be less expensive to go logically analyze what happened and go fix it, rather than go through the painstaking process of formally verifying it. Do note, though, that there is some overlap between the concepts of formal verification and testing. If you understand formal verification well, it can help you to write better or more meaningful tests that can start to target the same kinds of things that formal verification would be targeting. So we can ask questions like, can we generate test cases that trigger each line, branch, or path through the code? You have a large scale if statement or a big switch. What do you need to verify that? So you could query and say, here's some code. Could you write a program that automatically writes tests for it? It could analyze the code and say, here are the examples that fully test every path through this code. So here's an example. Let's say we write some tests in C++, because why not? So we're going to query, what is your name? If the name is root, meaning that they should have root power, then we grant them root access. Let's say we don't test this, and we test this. What are some issues that could arise? We have not verified. We don't have any understanding of what happens if someone's supposed to have root access to something. What happens if we don't allow root access to something, or if there's a crash associated with the root access to something? Probably something worth testing. All right, we will pick this back up tomorrow for not too long. I'll try to come up with, there's very little left of this, and this is the last thing that I really want to cover. So maybe there will be some time to work in class tomorrow. Ask me some questions, bounce some ideas off me. So see what you can get done ahead of tomorrow, and hopefully I can be useful. The end of class tomorrow. I apologize for the long and boring time.
I